My name is Niki Loppi, and I'm a solutions architect with Nvidia. I'm based in Helsinki, where my main responsibility is to help academics to accelerate their research using our technologies. My background is in computational fluid dynamics, so I'm very excited about scientific machine learning. This is the introductory lecture for the Scientific Machine Learning Bootcamp, where I talk about physics-informed neural networks with Nvidia Modulus. Before we start, I'd like to give a shout out to the Nvidia Modulus development team, Mohammed Nabian in particular, as I've reused several of his slides. So what is Nvidia Modulus? Nvidia Modulus is a framework for solving science and engineering problems using AI. The main idea of Modulus is that you can build a parameterized neural network model that is constrained by physical laws or data of them. Then you can just simply train the model once using massively parallel modern GPU architectures, and once you're done with the training, you can explore the parameter design space and infer new results in real time. I would like to also emphasize that today, Modulus is more like a framework or software suite rather than a single solver technology or neural network architecture. So it offers easy-to-use APIs and other building blocks for developers to use it for a wide range of applications. So let's now see what you can do in Modulus via a few examples. So first and foremost, Modulus is a partial differential equation solver. So similar to traditional high-performance computing solver technologies like finite element method techniques, finite difference methods, Modulus can solve partial differential equations without any external training data. You simply just give it a set of governing equations, the domain, and boundary conditions. The main difference here is just a lot of these traditional solver technologies distribute the solution using a predefined grid and compute the derivatives using numerical differentiation schemes. Modulus, on the other hand, solves the partial differential equations in a mesh-free fashion using a point cloud, such that neural networks learns the solution and partial derivatives are calculated via auto-differentiation. This is what we call the physics-informed neural network approach. Here you can see an example case where Modulus has been used to solve the linear elasticity equations brackets deflection example. So basically, there's this wall-mounted bracket and some force is applied to it, and Modulus can solve the deflections and stresses in the object just like a commercial finite element solver would. And the results almost perfectly match the commercial solver. So to the physics-informed neural network solution approach for partial differential equations, Modulus is an excellent tool for design optimization and design space exploration. So in product development or research, it's normal that you want to study different designs or the product under different configurations. With conventional solvers, you would have to undertake multiple simulations and build a surrogate model based on these data points to explore the design parameter space, and often then repeat the process in sequence to refine the surrogate model by undertaking more manual simulations in areas which you may find promising. With Modulus, you can simply just parameterize the system already during training time by simply adding the design parameters as extra inputs to the neural network. And when you have completed the training, it's super quick to do design optimization and design space exploration because you can infer new results from the trained model in near real time. Below, there's an illustration of an airflow and heat transfer simulation over an FPGA heatsink. With Modulus, you could, for example, parameterize the height of these heatsink fins during training time, and then at inference time, you can really quick find the best design that maximizes the heat transfer out of the FPGA. Modulus is also a solver for inverse problems. In certain science and engineering applications, you may want to infer some unknown system characteristics or variables based on external training data, for example, from sensors, imaging, or traditional HPC simulations. So on this slide, you can see an example of a case of flow over a two-dimensional cylinder. During training time, the neural network has been shown passive scalar concentration fields. If this data-driven loss is then also combined with the physics-informed loss of the governing equations, in this case, which are the Navier-Stokes equations, it allows us to infer the unknown velocity and pressure fields directly from the passive scalar field. Modulus is also a tool for developing digital twins. Digital twins are virtual representations of real-world physical systems, which normally are continuously updated via a stream of data, and they should predict the future states under varying conditions very quickly to allow interactive use of these models. So basically, it combines the parameterized physical solution and stream of data. Weather modeling is a good example of this. So future states should satisfy the governing equations, and you can give it also the real-life wind measurements history as an extra constraint. Modulus implements a lot of technologies that helps you to build this type of digital twins, and it also interfaces very well with Nvidia Omniverse technology. Finally, Modulus is also a tool for developing purely data-driven solutions to science and engineering problems, thanks to its variety of useful APIs. So instead of building your models, loaders, helper functions, etc. from scratch, you can start building the models with existing technologies and implementations in Modulus. Let's now put it all together. The figure at the bottom tries to illustrate the full spectrum of Modulus's capabilities and where it sits relative to traditional numerical solvers. So with Modulus, you can train purely physics-driven modules, which is in the schematic on the extreme left. In this case, Modulus would act as a partial differential equation solver with parameterization capabilities. If we look at the extreme right in this spectrum, where we have massive amounts of data available but no physics, then you could also use Modulus to build purely data-driven models. And then in this case, Modulus would act as an AI framework. Then in the middle, you have models, which combine both physics and data-informed learning. And they have particular relevance in developing digital twins and solving inverse problems. Let's now look at some theory of physics-informed neural networks. The main idea in physics-informed learning is that you use a neural network model to approximate the solution to some partial differential equation. As an example, let's now consider the Navier-Stokes equations, which call fluid flow. So as a first thing, what you need to do is to specify a domain where you sample the solution using a point cloud, which is illustrated there on the left. And in this example, this domain would be a two-dimensional channel with this circular section in the middle. Then you also need to define boundary and initial conditions. For example, what is the velocity that the fluid enters to the channel? And the velocity must go to zero at walls, which is called no-slip condition. Then also before training, you can set up parameterization to the network. For example, this radius of the circular obstacle in the middle could vary during training time. Then during training, basically you just simply pass the coordinates of your point clouds, the points in your cloud, to the neural network together with the design parameters, and the neural network outputs the field variables of interest. In a fluid flow case, it would be x-directional velocity, y-directional velocity, and pressure. Then, using auto-differentiation, you can compute the partial derivatives of your outputs with respect to the inputs. So terms like du dx, dv dy. And using these terms, you can encode the partial differential equations to your loss function. And then when the network trains, it minimizes the loss function, and then it effectively solves the PDE, and the neural network learns to represent the solution. Let's now look how you formulate the loss function in practice. Let's consider an example problem in one dimension as equation 1. Basically, we have a solution variable u, and the equation is the second derivative of u with respect to x must be some right-hand side function. And then we also have two boundary conditions requiring the solution to be the domain edges. Then, as mentioned before, now we want to represent the solution u using a neural network, for example, a deep multilayer perceptron, and the solution using this deep multilayer perceptron is denoted by unet. And please also note that as we want to compute higher derivatives, we also need to use action functions and continuous derivatives. So once we have the neural network in place, we can construct the loss function that we want to minimize. The loss function is constructed in parts. In equation 2, we have encoded conditions, basically just requiring that the neural networks gives a zero output at an output value of 0 at the domain edges, where x is equals to 0 or 1. Then in equation 3, we have the residual loss inside the domain. For this loss, we sample the solution along the domain, compute the second derivatives using auto-differentiation, and construct the loss as a mean-squared error. The equation 4 just shows that the total loss that we want to minimize is the sum of the boundary condition loss and the internal residual loss. If we use a constant function 1 as the right-hand side function, we have an analytic solution that is shown there in orange. And you can also see that we can get exactly the same answer using the physics-informed neural network approximation. So as mentioned before, one important advantage of a neural network solver over traditional numerical methods is its ability to solve parameterized geometries. To illustrate this concept, we solve a parameterized version of the problem, the 1D problem before. And suppose we want to know how the solution to this equation changes as we move the position of the boundary condition u at L equals 0. And we can parameterize this position using a variable L that varies in range from 1 to 2. To solve this parameterized problem, we can have the neural network now take L also as an input. So we have a unet which takes in now x as well as L. And then the losses take the form as shown in the slide. Let's now consider an inverse problem that is related to the original equation. So in an inverse problem, we start with a set of observations and then use those observations to calculate the causal factors that produce them. To illustrate how to solve inverse problems with a neural network solver, we now here it's given an example of inverting out the source term fx from the same equation as before. So suppose we are given the solution u true, so the ground truth, at 100 random points between 0 and 1. And we want to determine what is the right-hand side function fx that is causing it. We can simply do this by creating two neural networks, unet and fnet, to approximate now both u and f. And these networks are then always to minimize the loss shown above. Now I will highlight the standout features of Nvidia Modulus, what makes it so extremely useful for scientific machine learning. Firstly, Modulus includes a collection of partial differential equations written in symbolic math using SymPy. You can see the full list there. So if you want to solve, for example, a fluid flow problem, you can simply just import the Navier-Stokes equations. Alternatively, user can also define custom PDEs. Here, for example, Poisson and surface flux equations written in symbolic math. Secondly, Modulus includes a collection of neural network architectures, and you can see the full list there. User can import these architectures for their examples as a one-liner, or alternatively, user can also define custom architectures. Thirdly, Modulus implements very extensive geometry modules. The constructive solid geometry module allows to create object primitives and perform Boolean operations to them. So computes the signed distance functions, its derivatives, and surface normals. You can see the supported geometry primitives, Boolean operations, and other functionalities on the slide. The CST module also allows the parameterization of these object primitives. What's very cool is that Modulus also allows you to import complex tessellated geometry using STL files. And the Modulus uses ray tracing to compute the signed distance function fields and its derivatives, and also compute surface normals. And once the geometry is imported, it creates the point cloud for training. Finally, to bring it all together, Modulus implements constraint modules. So in Modulus, different loss terms are defined by constraints, and Modulus contains various types of constraints which are listed there. So basically, using constraints, you can enforce the governing equations on top of the geometry modules. And this is what your typical Modulus training script would look like. So first, you need to define your governing equation. In this example, we use a custom partial differential equation using SymPy. Then we instantiate the neural network architectures. In this case, we use a fully connected neural network. Then we import the geometry using an STL file. And finally, we use a pointwise boundary constraint to constrain the governing equations on top of the complex geometry surface. And then we bring it all together in a solver class and start the solver using solver.solve. The first example is the conjugate heat transfer case of an FPGA heatsink that was briefly also shown in the slides. So this is basically combining the incompressible Navier-Stokes equations for the flow and heat diffusion for the equations for the heat transfer. This case is particularly challenging because the thin fin spacing causes sharp gradients, and it makes it challenging to learn the flow inside them. However, with Modulus, we can use the signed distance function to downweight the areas of massive gradients to improve convergence. And we can also improve mass conservation by introducing these integral continuity plays to the channel. And these technologies allows us to tackle the problem better. And this case was also using a zero equation turbulence model. And from the bottom there, you can see that we can get results that are very close to those obtained using OpenFOAM. And here's a similar problem, but now we have a much more complicated geometry, which is also parameterized by 9 different parameters. Unlike a traditional solver, a neural network solver trains with all these design parameters in a single run, in a single training run. And once the training is complete, inference can be done basically in real time. So it's very quick to find the optimal design for the heatsink as a post-process. And by parameterizing the geometry, modules can often accelerate the design optimization by orders of magnitude, especially in cases where you have several design parameters. At the moment, I am also developing a 2-dimensional virtual wind tunnel for studying different airfoil designs. This is still work in progress, but how cool would it be that you could simply train a single neural network model without any external training data, which is parameterized by the thickness of the airfoil, the camber of the airfoil, which is basically the curvature, and also the angle of attack. And then in real time, it could give the flow field and compute how much lift and drag the airfoil design would produce. And here are some of my preliminary results where I only have the angle of attack parameterization and only use the zero equation turbulence model. This animation here shows the x-directional field together with streamlines. I could simply just train the model once, and then I can visualize the result for any in real time. And here's the animation for the pressure field. I'm using the same model to query the result for the pressure. Finally, here's an example I've used Modulus to simulate unsteady flow over a two-dimensional cylinder. Modulus has two different approaches for simulating time-dependent problems: the continuous window approach and the moving time approach. Here I've used the moving time window approach. In this approach, we basically simulate the problem using a sequence of neural networks. Each network is only for a subset of the total simulation time. In this case, the flow field starts to oscillate, and we call this the von Karman street. The vortex shedding frequency of the case depends on a dimensionless quantity called the Reynolds number. So basically, if you decrease the viscosity in the simulation, the vortices should start shedding with the higher frequency. I have parameterized the previously shown case with respect to the Reynolds number, and this plot shows the results. RE on the x-axis stands for the Reynolds number, and the ST on the y-axis stands for the Struhel number, which is the dimensionless vortex shedding frequency computing a fast Fourier transform from the unsteady flow field. The orange dots are my results computed using Modulus, and the blue line is a reference result from literature. You can see that they agree very well. What's very cool again is that I could simply do the training once, and then at inference time I can do the animation and compute the values like Struhel number interactively, because inference is so fast. So that concludes the lecture part, and now we can move on to the hands-on exercises. Thank you very much.